In a true vacuum, there is absolute silence. Without physical matter to act as a medium, sound simply cannot exist. But when a solid object, like this tuning fork, strikes a surface, the impact forces the metal to vibrate, violently pushing against the air. That initial physical disruption transfers kinetic energy outward. The vibrating object forces the nearest air particles into motion, driving them to collide with their neighbors. What we perceive as a noise is actually this temporary chain reaction of mechanical energy fighting to travel through a physical environment. This diagram illustrates how kinetic energy propagates. As a vibrating membrane moves forward, it shoves air particles into tightly packed clusters. These dark vertical bands are compressions. As the membrane retreats, it leaves wide, low-density gaps called rarefactions. Through this alternating pattern of compressions and rarefactions, the wave travels. The air particles themselves do not move across the room. They merely oscillate back and forth in their original positions, while the invisible energy travels forward. Since this process relies on particle collisions, the medium dictates the speed. In standard dry air, a wave travels about 343 meters per second. In water, it moves 4 times faster. Through solid iron, it tears forward at over 5,000 meters per second. A wave's survival, speed, and efficiency rely entirely on how closely packed the atoms are within the physical architecture of its environment. While every sound wave is a product of mechanical energy, the exact rate of the original vibration dictates its distinct acoustic character. We perceive this rate as pitch. A large animal's deep growl is produced by slow, low-frequency wave oscillations, while the rapid, high-frequency beating of an insect's wings creates a sharp, shrill sound. The standard scientific unit measuring these oscillations per second is the Hertz, named in honor of the 19th century physicist Heinrich Rudolf Hertz. If frequency determines the pitch, amplitude dictates the loudness. Amplitude is the measure of the shear kinetic force and the maximum physical displacement of the particles from their resting position. A massive vibration creates a high-amplitude wave carrying intense kinetic energy. At close proximity, a jet engine generates waves so forceful they can cause immediate physical pain and permanent hearing loss. Together, the frequency and the amplitude act as invisible mathematical coordinates, defining the exact identity and intensity of every noise we encounter. Yet, if you play the exact same pitch at the exact same volume on a tuning fork, on a violin, and a piano, they still sound remarkably different to the human ear. This chart reveals why. The top panel shows a tuning fork's perfectly smooth sine wave. The middle panel shows the violin's intricate, jagged structural complexity. The bottom panel displays the piano's drastically different, blockier wave architecture for that same note. This specific trait is known as quality or timbre. The complex physical geometry of the wave acts as an acoustic fingerprint, allowing our brains to instantly identify the mechanical origin of the sound. As these waveforms travel outward from their source, they eventually collide with physical barriers in their environment. Much like light bouncing off a mirror, a longitudinal wave striking a dense, hard surface will reflect back, with the incoming and outgoing waves mirroring the exact same angle against the boundary. If you stand far enough from the reflecting surface, you hear this return journey as an echo. The human brain retains a sound for about 1/10 of a second, meaning there must be at least a 0.1 second delay between the original event and the reflected wave for us to perceive them separately. A distinct echo is a direct measurement of distance, mathematical proof of the wave's physical journey across the environment and back. Since sound operates at a measurable speed through air, an aircraft accelerating toward that limit forces a unique physical confrontation. As a supersonic aircraft accelerates, it constantly emits mechanical energy. Moving near the speed of sound, the craft begins catching up to its own waves, causing the compressions to pile up directly in front of it. These overlapping compression pulses merge into an inescapable wall of concentrated, high-density air molecules, violently resisting the nose of the plane. When the jet finally accelerates past this intensely compressed wall, it shatters the barrier. The massive release of overlapping acoustic energy unleashes a single continuous shockwave known as a sonic boom. Through vibration, transmission, and reflection, sound maps out the invisible architecture of our reality. But when pushed past its absolute aerodynamic limit, that mechanical energy concentrates into a sheer physical force.